for joining. We've got two presentations today, both on different aspects of atmospheric moisture. I think Caitlin agreed to go first. So Caitlin is a PhD student at Penn State, and she's going to first talk about some work that she's been doing in terms of precipitation. I think around 20 minutes. Then we'll have time for questions after that. And then Isabel Horst from Hopkins is going to talk about dry islands. So I don't want to, Caitlin, you can take it away.
Cool. Thanks, Darren. Let me just share my screen. If I put this in present mode, can we all see it still?
Yep, I can see it.
I can
Awesome.
see it.
Thank you. So, I think most of you are pretty familiar with what I do, which is nice. But today I'll be talking about how we can use dual pole radar rainfall measurements to understand precipitation trends in the coastal mid-Atlantic. This is sort of adapted from a talk that I did for a weather, climate, and society class, which is focused on communication with the general public. So a lot of this is kind of an understanding of how does radar work and how we can use it, and some examples of that to understand precipitation. So that's my goal today. So if any of that doesn't make sense, please feel free to ask. Oop, click. So it's important to understand when and where heavy rain falls because heavy rain can cause flooding. It's one of the key drivers of pluvial flooding in areas that have a lot of impervious surfaces, such as concrete and urban development. This is important in the coastal mid-Atlantic because it's home to two major metropolitan regions, Baltimore and Washington, D.C. This region is also particularly interesting because it has so many complex topography features, such as the Chesapeake Bay, complex coastlines that you can see off to the right here, proximity to the ocean as well, and the Appalachian Mountains. And these features are known to generate mesoscale circulations or small scale atmospheric processes that can locally intensify rainfall rates. So, because of this complex topography and coastlines within the mid-Atlantic, it is important to understand when and where heavy rain may fall so that we can get an idea of the physical processes that dominate heavy rainfall in the region. Just an example of a couple of these are downslope winds, so something that can happen given the proximity to the mountains in the mid-Atlantic region. As you have winds in broad terms that come down off of mountains, they can generate these atmospheric waves, which we can't see, but what they can do is they can create clouds. These clouds can then cause rainfall and thus impact our study region. Something that we're probably a little bit more familiar with are sea and bay breezes, which are small scale circulations that are developed between differences in surface heat from the Chesapeake Bay or the Atlantic Ocean, which might be cooler, to land in the summertime, which is going to be probably warmer, at least during the day. These circulations can also intensify and generate rainfall. You put even just these two things together, barring any other mesoscale features that might occur within the region, and the dynamics already get really complicated. So, we need to understand what the general distribution of rain is in space and time across this entire domain to get a sense of the dynamics that could influence rainfall. We can do this by using weather radars, and prior studies have used weather radar to do this, which I'll talk about in just a moment. A weather radar, when you pass by it, looks kind of freaky and maybe a little alien spaceship-like. If you don't really know what it is, so here's a picture on the left-hand side showing you what a radar looks like. And it kind of just looks like this big ball, and you can't really see what's going on with it. Within that big ball or this radar dome, which is essentially just protective, it protects this instrument that is similar to like a satellite dish that you might have on your roof, right? Where you have an antenna and this dish that can emit radiation and receive radiation. So, as I mentioned, radars emit energy, and it is in the form of waves or atmosphere or electromagnetic radiation. It kind of has a lot of different names that people use, but the main point here is that they are harmless. And what they can do is they can slice through essentially clouds and precipitation within the air surrounding the radar. They're emitted at an angle above the surface so that they don't just keep like hitting trees and mountains and things, and they can measure processes that are happening kilometers up into the atmosphere. When the radiation hits some of these droplets and clouds, some of the radiation gets sent back to the radar. Some of it gets scattered out into the surrounding environment, and some of it can move forward through the radar as well. Using the energy returned to the radar, we can determine cloud droplet information to create radar variables such as reflectivity, which is essentially a measure of how much energy is returned to the radar. There are many studies of rainfall in this region in the past 10 to 20 years that have used reflectivity to identify rainfall. Natelikos et al. In 2008 used Titan to track storms using reflectivity and also used reflectivity in tandem with lightning frequency to study storm intensification as a thunderstorm interacted with the Chesapeake Bay. Smith et al. In 2012 developed this really nice high-resolution radar rainfall data set using bias correction processes from rain gauges, and I'll talk about why they needed to do that in just a second here. In 2024, they expanded upon this climatology and introduced the use of more dual pole radar variables for the last kind of half of this 22-year period to create an even longer climatology to analyze rainfall in the Baltimore region. But reflectivity does have a minor issue, and it's that it is power dependent and it suffers from attenuation. These papers do note that, and they note that you kind of require a rain gauge bias correction process to enhance the reliability of reflectivity measurements. Brandis et al. In 2001, however, indicated that rainfall estimates from this bias-corrected reflectivity using rain gauges are comparable to rainfall estimates from a different radar variable called specific differential phase. So we can use KDP, specific differential phase, to generate a reliable, high-resolution radar rainfall data set that we can use in regions with and without rain gauges, such as offshore, or a region that just might have sparse surface observations. This introduces the need for dual pole radars, which luckily for us, we have dual pole radars that we use operationally as of 2013. So we have 13 years of this data. And how a dual pole radar works is that it emits energy in both horizontal and vertical planes. This allows us to get a vertical and horizontal measurement of clouds and cloud droplets. So radars can gather information about cloud droplets in both of these dimensions. If you zoom in, that's kind of what it'll do for a raindrop. And we can use this information to derive specific differential phase, or KDP. And it can tell us a lot of stuff. It tells us about the rainfall or raindrop shape and raindrop distribution, or how many raindrops might be within a small area. It's at a base level, just using the signs, relatively easy to understand in relation to the shape of the raindrops that we might have, or shape of atmospheric particles, I should say. So when KDP is negative, particles are taller than they are wide. So think something like a columnar ice crystal, which if you see those pictures of ice crystals, it's like the ones that look like needles, right? So that's when you would get a negative KDP. If you had a drop that was perfectly circular, which usually never really happens, you would have a KDP of 0. And when you have a particle that's wider than it is tall, kind of like a hamburger shape, this is usually how raindrops fall in the atmosphere. You would get a positive KDP. And we can take this KDP value, it's in degrees per kilometer, and we can actually just convert that to millimeters an hour to get a sense of rainfall rate using this equation from Richkoff et al. In 2005. So we can then use this dual pole radar, or dual pole radars in general, to measure heavy rainfall in regions without rain gauges. So just an example, if you take heavy rainfall or intense rainfall of 20 millimeters an hour, you plug that into this equation, you rearrange it a little bit to find the backtrack it and find the KDP. You'll get a positive KDP, which indicates that particles are wider than they are tall. You have these fatter raindrops that are large in quantity. So we can use this rainfall equivalent KDP to generate a climatology of heavy rainfall for the 10-year period from 2015 to 2024 for the warm season, when a lot of these mesoscale processes that I talked about at the beginning are most prominent. We look at 8 subregions of interest in our study across 2 radar domains here. We can investigate the inland region, the coastal region and the offshore region. We do this qualitatively and quantitatively separately. This is important to get this full range because we can understand what's happening over the Appalachian Mountains, offshore over the Atlantic, and within the coastal region. Current studies or prior studies are kind of just limited to this near coastal region within the Chesapeake Bay, and expanding it can give us a better picture of what's going on. So we can start off with a very basic frequency analysis of KDP that is equivalent to rainfall rates of 20 millimeters an hour or higher to get a sense of where the heaviest rainfall does fall in the summer months. So this figure is kind of the structure of this figure is what I'm going to be showing throughout the course of this talk. On the left-hand side, we have our measurements from KLWX, which is the radar in Sterling, Virginia. On the right-hand side are measurements from KDOX, which is at the Dover Air Force Base in Delaware. And we do this all of our analyses separately for June, July, and August. What we find is that we have the highest frequency of this intense rainfall of 20 millimeters an hour or higher within our coastal region. So east of Washington, D.C., and kind of west of the coastline here. We also do see some heterogeneities that pop out month to month. So we have a hotspot of high heavy rainfall frequency in southern coastal Virginia in June. It becomes more widespread in July, but we do see some really prominent coastal gradients here of heavy rainfall frequency. And in August, we do see that in general, the frequency does decrease, but our hotspot shifts upward, northward toward southeastern Pennsylvania. We also do see that heavy rainfall is generally more frequent in the onshore environment than it is in the offshore environment. We can also look at this hourly as well to get a sense of when this rain is occurring. And this is a plot of the sum every single hour of heavy rainfall frequency for the entire region in each year. We do see a diurnal cycle pop out in many of these years where we have most frequent heavy rainfall in the afternoon, and then we reach a minimum in the early morning and overnight hours here. So heavy rainfall is a bit less frequent at those times. And we do see a great deal of interannual variability where some years are much more intense than others. Some years, like this one right here, 2017, are relatively flat, right? Some of this is driven by data availability. There's just a lot of data missing for this year in this month. But it can also be driven by impactful weather events, such as in June. Here we had the remnants of a tropical cyclone. It weren't tropical cyclone structure, but they still brought a lot of rain to the region. So I just want to remind you of these subregions of interest because we can repeat this analysis, but separating all the data into our different subregions to get a sense of the impact that different land surfaces or geographic regions might have on heavy rainfall. When we do this, we summed the KDP frequency in each of these subregions, we separated it by each hour of the day, and we normalized it by the number of data points in each region. What we get is a pronounced diurnal cycle for these green and brown lines here, which represent our inland and our coastal regions, where heavy rainfall is highest and increasing during the day when it's yellow here, and it's decreasing and reaches a minimum through the overnight period as well. Very kind of responsive to boundary layer development and growth. We also do see that the coastal subregions, these green lines, are often have a higher frequency of heavy rainfall than the inland regions. And we also don't really see much of a diurnal response or high response of heavy rainfall in the offshore regions here either, which is interesting. When we take the mean of all of these data points at all of these hours for the number of times that we have heavy rainfall in each hour, we can generate a mean precipitation hour plot showing sort of a tendency of when rain falls across our entire domain. We find that the mean precipitation hour during the day is during the day over land here, where we see these brighter, more orangey colors. The white color is 0 UTC, or roughly sunset in the summer, and the blue is overnight. So we can see that it's generally during the day over land and overnight offshore. But I do want to remind you that offshore we don't really see much of a diurnal cycle, so you kind of have to take that with a grain of salt. We also see this gradient from northwest to southeast over the land where the mean precipitation hour is a bit earlier in the northwest and a bit later in the southeast. So to recap thus far, Heavy rain is most frequent in the coastal region compared to our inland and offshore subregions, and it generally falls in the afternoon and evening hours over land, which correspond with our daylight hours. This tells us that there's some kind of dependency on daytime land surface heating for heavy rainfall, um, maybe a process similar to or directly related to that of the boundary layer growth. So we know when and where heavy rain falls most frequently now, but we need to get a general sense of the intensity of rainfall. So if we consider all rainfall greater than 10 millimeters an hour, what percent of that is due to this heaviest rain that we've been looking at, this 20 millimeters an hour or higher? We can do that by calculating a simple percent contribution of the heaviest rainfall of 20 millimeters an hour here to everything above 10 millimeters an hour. So that's what's represented on the right-hand side here for all hours of the day. And then we also see for our inland and coastal region, we have a higher contribution from this more intense rainfall in the afternoon and evening that then decreases through the overnight hours and into the early morning. And this is consistent across all three summer months for our coastal and our inland subregions, so our green and our brown lines here. We sort of see the offshore subdomain kind of follow the coastal subdomain for our more coastal radar. This could be due to just the way that I sampled the different subdomains there. And just remember that there's not as much rainfall there, nearly as much rainfall in that region as there are in the other two. Um, and rainfall is also consistently heavier in the coastal region than it is inland. While they do have peaks of about the same contribution from this more intense rainfall, in the overnight hours, the coastal region does have a higher contribution from this heaviest rainfall in all three of our months. So from this, we can determine that the coastal mid-Atlantic receives the most frequent and heaviest precipitation in most hours of the day compared to our inland and our offshore regions, kind of a callback to our spatial plots here and our hourly frequency plots as well. Due to the timing of this maximum rainfall frequency as well as the spatial distribution of it, this tells us that mechanisms known to impact precipitation generated by mountains and coastlines are likely causing this increased precipitation frequency in the coastal mid-Atlantic and Baltimore region. We also see, as I just mentioned, we do have a dependency on this daytime period for generating heavier rainfall, where we have a higher frequency of heavy rainfall in this period, as well as a higher contribution from precipitation greater than or equal to 20 millimeters an hour in our terrestrial subregions, so the inland and coastal domains, as compared to our offshore region. This tells us directly that diurnal surface heating is something that really drives heavier and more frequent rainfall during the day than in the overnight period. So I'm a little bit quick on that. However, I am happy to entertain any questions.
Thanks, Caitlin. So do we have some questions?
Okay, then I have one question.
Yeah.
Um, Thanks for the talk. If you can go back maybe one slide or so. Actually, one more for your conclusions. Yes, that one.
Mhm.
Um, it's something to notice, like with the plots. If you line up, like say on the top row where you're lining up like Baltimore and DC, they're different values. It's not it's a little muddled, but there are different preset values, I guess, for where the cities are. So I'm guessing I'm just curious about how you resolve which radar observations to trust in that situation, mainly because it seemed like it also propagated to the mean plots that you show, like where one of them had a stronger gradient over land versus a weaker one. So I'm just curious how you resolve that.
Yeah, that's a great question and an important one. Um, so just with the way that these two radars sample, right, they are sampling different layers of the atmosphere slightly
Mhm.
at different heights and distances from the radar. And I do have a plot of that here. Um, So, for example, over DC from your Sterling radar, you're only at about 500 meters above the surface, which oftentimes is below your cloud base.
Mhm.
Whereas from your Sterling or your Dover Air Force Base radar, you're at almost 2,600 meters, right, which is within your cloud probably. So that's something to keep in mind, and it could slightly change the KDP that you're seeing maybe aloft in the cloud versus lower to the surface. There is also different data availability at each of these radars. That could also be contributing to this. One radar might miss a really significant event where the other one doesn't. And this is kind of like a caveat with using these operational radar measurements, right? Sometimes they go down for maintenance, or they're just broken, or the measurements aren't reliable. And so we're actually missing a whole bunch of days for various reasons or hours for various reasons. And they differ across the radars, right? And we wanted to keep all the observations that we could. So that's why we didn't like if one thing is missing from one radar, we didn't remove it from the other one because over a 10-year period, generally this does kind of get flushed out, but it does generate some of those heterogeneities between the two radars that you picked up on. Is that kind of helpful?
Yeah, gotcha. And thanks a lot for that. And that's just on the right track. You're still looking, you're not necessarily looking at one level of the radar, you're still looking at total column.
It's not necessarily
Yeah.
total call. It's a single tilt, but
Okay.
the radar tilt does change with elevation. So as you get farther from the
Gotcha.
radar,
Yep.
the beam will be higher in the atmosphere and it also broadens. So it will sample a larger selection of the atmosphere. So
Hmm.
you can interact with regions such as the melting layer where you have kind of this mixed phase precipitation. And with KDP, that can actually be, um, it make KDP at lower values appear a little bit enhanced, just due to kind of some of the shedding that you get as ice particles melt in the atmosphere. So you kind of have to like interpret everything relative to where the radar beam is in the atmosphere.
Okay. Got it. Thank you.
Yeah, and that's why it's helpful to have both too, so you can kind of cross-reference.
So, Caitlin, I see Ken's got a question, but I'm speaking now, so I'll jump ahead of you, Ken. So, um, how, if you wanted to focus just on like the Baltimore region, can this data, if you wanted to see, okay, how does the precipitation vary at, the Baltimore and surrounding area to see, is this data good enough to do that? Or could you look at it to see what the spatial variation is across the city or whether there's any difference between the city and the surrounding areas? Do these storms kind of break up because of the city or things like that?
You could, and the studies that have been done have more of that city focus. So like the Smith et al. Papers have a really nice description of the distribution around the city. You could use this variable to repeat that analysis as well. Um, if I were to suggest something, if someone were to do that, there are multiple radar tilts available that can give you a really nice picture of the total column, kind of like Elliot mentioned, of the clouds and precipitation. And you can actually you can just get a better picture of like the KDP core, this heavy rainfall core of the storms. That would probably lead to a really nice local analysis for the region, if that answers your
So,
question.
so what does Smith et al. Show?
They show that the precipitation to the northwest of the city they generally see more precipitation along that Chesapeake Bay coast and less precipitation more inland to the southwest of the city. And they also show the similar diurnal cycle that I show as well. They do suggest that circulations generated by the urban heat island could be at play in determining this, but also that a lot of it's modulated by the Bay breeze and Chesapeake Bay impacts as well.
Yeah. Okay, thanks.
Yeah.
Okay, Ken, seeing as I jumped in.
Oh, that's all right. I had a related question, and I think, Caitlin, the enhanced precip in Smith is to the northeast.
Oh, it's totally to the northeast. I just read the
Yeah,
paper yesterday. Yeah.
you said northwest.
Yes,
Northeast, I think
thank
is
you.
what you meant. Yeah, got it.
Yeah.
Now, I had a kind of related question, and I think I know the answer to this, but I just thought it'd be useful to make sure. Um, this is you're using KDP so you can focus on the heavy precip events, right? This is not the normal reflectivity we would see looking at a radar image on our phone, correct?
Correct.
Okay, and whereas the Smith et al. Work is just total precip, correct?
Yes, it's just total precip. This is
Yeah,
just
so
on heavy
so
event.
I just wondering how much are those different? It's similar to Darren's question. You've got the intense precip. Smith et al.'s got the total precip. How distinct are these?
You mean
How
in
different?
results?
It seems like I'm going to guess your results show that the heavy precip is more coastal,
They do.
whereas
Um,
the overall precip doesn't show that really strong coastal structure. Don't know.
in my observations and the way that I've kind of seen this, the Smith et al. Papers do note this coastal gradient, and that's something
Okay.
that I noticed as well in the total precipitation, um,
Okay.
which makes sense because with your sea breeze, you might get a shallower cloud that has some lighter rainfall, right? If that is what's modulating your precipitation. But
Okay.
we also do see, if I can zoom in here to make sure. You do have, at least from one of these radars, this hot spot to the northeast of the city, right? That is very
Okay.
similar to what they see for July in the Smith
All
papers.
right. So you're saying at first glance they're not dramatically different.
Right. Yeah. I
And
think that in order to get a really nice analysis of that local region, I think that this study could be a bit more thorough. But for the purposes of the study, we're focused more broadly. But you do see that coastal gradient, I think.
okay, thanks.
Mhm.
Yeah, I do have a question. Yeah, looking at the process of KDP, can it be applied to a futuristic scenario to understand, probably the precipitation in coming years? Is it possible to do that?
So all of this is observation based. Um, I'm not very familiar with studies that have simulated KDP in a future climate scenario. Um, I feel like it could be done using different microphysics schemes to estimate raindrop size and orientation as it falls and the same kind of KDP rainfall process. Um, I haven't seen anything that has done that if it is out there. But it would be something kind of like your simulated reflectivity in WRF, right? You would just simulate KDP instead. If that is that kind of what you were getting at?
Yeah, exactly. Well,
Yeah,
that's right. Yeah. I'll look at it.
I think it could be helpful.
Yeah, thank you.
Hmm.
Okay, well, thanks, Caitlin. That was great. That was just at my level. Needs to be
For
very
sure.
introductory. So, um, okay, thanks. So now we'll hand it over to Izzy, who's going to talk about the dry island.
Hello, is everybody seeing my screen?
I can see it.
Okay, great. So yeah, today I'm going to be talking to you about the urban dry island effect in Baltimore. Excuse me. This is work that I've been doing over the last couple months using the our lovely weather station network and all those meteorological measurements. So yeah, let's get into it. Oh, where's my pointer? Okay, so I'm going to start with a bit of just background motivation for this work, and also some of the scientific basis. So at this point in BSEC, you're probably aware that urban heat extremes are a growing concern. We are familiar with the urban heat island effect, where cities tend to have higher temperatures than their surrounding rural areas. And this can be hazardous to our health because an increasing majority of the world's population lives in cities, and extreme heat has a lot of negative health effects. It also hurts our infrastructure, means we need more energy to cool our homes. And then there's also intra-urban variability within a city where very frequently the burden of extreme temperatures falls disproportionately on neighborhoods with high socioeconomic vulnerability, like this plot shows for Baltimore. And so a lot of studies have been done linking surface temperatures or some air temperatures uh, to socioeconomic vulnerability and things like redlining. And then also in the future, urban heat is a growing concern because not only is the Earth projected to warm, but also the cities themselves are growing, and the fraction of the world population that lives in cities is growing. So in the future, an increasing amount of the world's population will be affected by urban heat extremes and urban climate in general. But I'm not here to talk to you about temperature. I'm here to talk to you about humidity. So the Earth is also getting wetter as it warms. This image is showing across the globe that for every degree Celsius of warming of normal temperature that we expect to see 3, 4, 5 degrees of warming in wet bulb temperature. And wet bulb temperature is just a measure of humid heat. And this is largely due to this Clausius-Clapeyron relationship shown here. So this shows that the saturation vapor pressure for water vapor in air increases exponentially with temperature. So this is a crude way of saying this is that warmer air can hold more water vapor. And I mentioned that high temperatures have a lot of risks for our health, our infrastructure. But when you add humidity to the equation, it kind of introduces some unique risks. So we as humans experience heat as a humid heat because we're sweating beings. Humidity can also have direct effects on our energy demand, how much energy we need to cool our houses. And also, it can affect things like labor capacity. Like, for example, in the US, we have OSHA, Occupational Safety and Health Administration, and they use wet bulb globe temperature, WBGT, which is a measure of humid heat, to set regulations about the number of breaks that outdoor workers have to take, depending on what the WBGT value is. And so this plot from that same paper is showing that with future warming, the population-weighted labor capacity across the globe is projected to decrease. So yeah, hopefully at this point I've convinced you that urban heat and especially humid heat is not only a current concern, but a concern for the future. So now a bit of the scientific background. A lot of you might be familiar with this if you know about the urban heat island, but the urban heat island effect really comes down to differences in the land surface characteristics between urban areas and rural areas that cause differences in the surface energy budget and the radiative properties between those two environments. So starting just with the surface energy budget, that is this partitioning of the energy coming off the ground surface into latent and sensible heat. And so latent heat is the heat absorbed by water when it evaporates. So in cities generally, and then sensible heat is just the direct dry heat transfer. And so in cities, generally the surface energy budget is partitioned more towards sensible heat. So it's more of that, like the heat you would feel if somebody was pointing a hairdryer at your face, or like you can sometimes feel the heat radiating off concrete. Whereas in rural areas, more of the surface energy budget is partitioned towards latent heat release, which we don't feel directly because it's the heat that's being absorbed by water as it vaporizes. And that's because there's generally a lot more surface moisture in rural areas. Also in cities, we have a lot more sources of anthropogenic heat, so things like car exhausts, HVAC systems, and we have all this concrete that is really good at sucking up all this heat over the course of a hot day, and then hanging on to it really tightly at night and releasing it slowly, so it cools very slowly overnight. Whereas in rural areas, generally the ground is able to cool a lot more quickly after the sun goes down. There are also phenomenon where tall buildings can sort of trap radiation between them, and it just keeps bouncing around, keeps warming things up. And we also have more pollution that is associated with heat in cities, whereas in rural areas, generally less pollution, and radiation is able to sort of escape the surface canopy layer more effectively. But again, I'm here to talk about humidity. So as sort of a corollary to the urban heat island effect, there's this urban dry island effect where cities can sometimes be drier than their rural surroundings. There's also sometimes an urban moisture island effect, but here I'll just be talking about the urban dry island because that's what really affects Baltimore. And so to sort of explain the theoretical basis for why this might be happening, I'm going to use this little cartoon atmosphere. So here's my little atmosphere. It's got water vapor droplets in it. It also has a temperature. It has a specific humidity. So that's an absolute measure of humidity that tells us by weight how much water vapor there is in the air. And it also has a relative humidity. And for my measure of relative humidity, I'm going to be using vapor pressure deficit, which depends both on temperature and specific humidity. And it is the deficit between the current vapor pressure in the air, so how much pressure water vapor droplets, water vapor molecules are exerting in the air compared to the saturation vapor pressure. So how much water the air theoretically could hold before it became saturated, or at the point it became saturated. So VPD, the larger your VPD, the more dry it feels. And so VPD is a relative metric. There are two ways we can change it. Well, two main ways. We could change the specific humidity by doing something like adding vegetation. This just makes more water vapor available to be evaporated into the air. So if we had a bunch of vegetation, that would increase the specific humidity, therefore increasing the vapor pressure of water in the air. And assuming the saturation vapor pressure doesn't really change, that shortens the vapor pressure deficit, and so it makes it feel more humid. Another way we could change VPD is to change the temperature. So if we increase temperature, remember that Clausius-Clapeyron relationship. With higher temperature, the saturation vapor pressure becomes higher, so warmer air can hold more water. And so if you increase the saturation vapor pressure by increasing the temperature, but you don't really add any more water to the air, so the specific humidity and vapor pressure stay the same, that means the VPD will increase and it will feel more dry. So in an urban to rural situation, the general contrast is in cities, we tend to have higher temperatures, fewer sources of water vapor, so lower specific humidity, and therefore higher VPD, compared to rural areas where we have generally lower temperatures, more sources of water vapor, lower VPD, so it feels more humid. So this is sort of the theoretical framework that I'm working with for how the urban dry island might work. And in Baltimore, we have this amazing wealth of observations from our weather station network. And so I wanted to look at whether or not we could measure a summertime urban dry island in Baltimore. So my first question is, does this even exist? How can we measure it? And then the two important follow-up questions are, how does it vary in time? So both over the course of a day and between days. And most importantly, how does it affect the spatial and temporal variability of humid heat, the type of heat that we as humans would feel and be affected by? So getting into data and methods, all of my meteorological measurements are coming from the Baltimore Community Weather Station Network, which is sort of grown out of the BSEC project. And I'm using about 45, well, not about, exactly 45 weather stations from June through August 2025. And I really love using these weather stations because it's a great community effort. And I really appreciate all the people who have put a lot of work into maintaining these weather stations, putting them up, using them to teach kids. I think it's really cool to be using sort of community-based observations for my science. Then I'm also using a land cover data set from the Chesapeake Bay program. So this is a snapshot of what it looks like. It's very high resolution at about 1 meter. This is it zoomed into the Hopkins campus, but this data set exists for the whole state of Maryland. And I'm using this data set because I want some sort of reference for what the natural environment or what the environment surrounding each one of these weather stations is. So this data set here, I've color coded it to where everything that's in light or dark gray or red is impervious surface cover. And I'll be using that impervious surface cover sort of land use category moving forward as a metric for urbanness. It's really tricky to define what exactly urban means. You can define it based on just space or by explicit land surface characteristics. And just cities are generally very messy, and it's hard to define where urban becomes rural. So I've chosen impervious surface cover from this land cover data set as my metric because the data is readily available, and it also gives us a measure of the local land surface characteristics around each weather station that we can tie to some sort of surface energy balance process. So to illustrate what I do with this data set, I'm going to zoom in here on the Zoo station and the Remington station. So for each weather station, I just place a 100-meter box around it and take the average of how much of that area is covered by impervious surface cover. So for the zoo, you can see it's generally lower impervious surface cover, whereas the Remington station is very high. And I think it's interesting how drastic the contrast is between these two stations because they're very near each other in space. So this is really a testament to how messy cities can be, how much the local environment, the characteristics of the local environment can change over the distance of like a kilometer. So yes, I do this for each one of the weather stations, and this is what the data looks like when you map it all out. So this is summer daytime averages for temperature, heat index, and specific humidity overlaid on the slightly coarsened map of the impervious surface cover. And if you kind of squint, you can already see a bit of a dry island. The specific humidity values are slightly lower in the middle of the city. And you don't have to just trust me on that visually. I'm going to explain it with numbers in a minute. But before I do that, I just want to highlight two pairs of stations that I've identified with special icons. So I have this pair that I'm using squares to identify, and this is sort of a very typical urban-rural station pair. So one is very far from the city, around lots of vegetation, very low impervious surface cover, and one is very much in the middle of the city with lots of impervious surface cover. So this is what the type of station pair that historically would be like a good candidate for defining an urban heat island or something like that. But then I've also chosen an atypical pair where one station is far from the city center, so we might want to call it rural, but it actually has a very high impervious surface cover. For anybody familiar with the weather stations, this one is the one at Beth DeFilo School, and then my atypical urban station is the one near the Courage site in Clifton Park. So this is my atypical urban station because it's quite near the city center. It's almost, it's very close to the Midtown East station. That's my typical urban station. But because it's in the middle of a park, it has very low impervious surface cover. And so pay attention to those squares and stars as I sort of move forward. So how do I actually define a metric for urban dry island, urban heat island, and urban temperature island? Before I explain that, I'm just going to explain this plot real quick. So these plots are showing on the x-axis, we have the impervious area fraction at each weather station. And then on the y-axis, we have the nighttime and daytime summer averages for temperature, heat index, vapor pressure deficit, and specific humidity. And right away, you can probably see some trends jumping out. So that's pretty much exactly what I've done. I've just put trend lines on these plots for every hour of data that I have using linear regression. So for the linear regression slope for temperature, change in temperature with impervious area fraction gives me the urban temperature island intensity. The slope for heat index gives me the urban heat island intensity. And just take note of that difference. I'm using UHI to refer to heat index, not temperature, as it's often used. So just important distinction between UTI and UHI. I use the slope for VPD to give me a relative dry island. And then I use the slope for specific humidity to give me an absolute urban dry island. And so to put this in words, what the slope means is it gives us the expected, the change that we would expect in specific humidity as you went from 0% impervious surface cover to 100% impervious surface cover. So like a proxy for fully rural to fully urban. And just visually on these plots, you can see it as the vertical distance covered by each of these lines. And I want to take a minute again to call out these two station pairs that I've identified. So just starting out with the typical urban-rural pair, if we look at these squares on, for example, the daytime heat index plot, you can see that if you were to rely on those two stations alone to define your UHI, you would get a really large value compared to what the linear regression slope tells you. And then on the other hand, if we were to use an atypical urban-rural station pair, for nighttime urban temperature island, we might see a warm island. So I just wanted to use those station pairs to really highlight how the choice of station and the local land surface characteristics around each station can really determine a lot about the climate that station measures. with a similar magnitude as whether or not that station is like near the city center or out in the suburbs, out in a rural area. So yes, so a real advantage of using all this data across an impervious surface cover sort of gradient is that it allows us to measure more intra-urban variability and tie it to a clear land surface characteristic. And the result is less sensitive to any one station having a weird day or having something specific about its land surface characteristics nearby. So what did I find? Baltimore does have an urban dry island. So these are diurnal cycle plots showing the 4 urban island metrics that I've measured. So just focusing on the top 2 plots, these are my urban dry islands. The absolute urban dry island is present really only during the day, throughout daylight hours, and then during the night it goes towards 0. Whereas the relative urban dry island, because it has this influence from temperature overnight, it stays relatively constant throughout the day in sort of a range from like 4 to 7 hectopascals. And then looking at the urban heat island and urban temperature island diurnal cycles, we see sort of the expected behavior where the urban temperature island and urban heat island are greatest at night and then dip down during the day. But if you kind of squint and look closely, you might notice that the urban heat island during the middle of the day gets closer to 0 than the urban temperature island does. And this is because of the influence from the absolute urban dry island. So in the middle of the day, during the summer, in these highly impervious, sort of highly urbanized areas, we might have slightly higher temperatures because of the urban temperature island effect, but we have also much lower specific humidity because of the urban dry island effect. And so those two sort of counteract each other and end up, the low humidity ends up bringing down the heat index such that the UHI gets kind of washed out. And that's not to say that there might not be spatial variability in heat index throughout the city. Just based on the way that I have defined UHI here, it's saying that we might not see any clear relationship with heat index and impervious surface cover because of these competing effects of temperature and specific humidity. So now I'm going to look at that a little bit closer. But first, I just want to remind you, these VPD and heat index are both relative metrics, and so we can break them down into their temperature and water vapor availability driven components. And I'm not the first person to do this. But when you do this, these plots are showing the same diurnal cycles as before, where the solid line is the diurnal cycle in UHI and relative UDI. But these lines have been broken down into their temperature-driven component in light blue and their water vapor-driven component in this sort of teal color. And so you can see that for the UHI in the middle of the day, the values are being sort of pulled towards 0 by this lack of water vapor in highly impervious urbanized areas. And so the specific humidity and temperature components are almost perfectly canceling out. And then for the relative dry island, dryness and high temperatures add together instead of cancel out. So in the middle of the day, the relative dry island is about 40% driven by absolute humidity. And then for both of these during the night, it's almost entirely driven by temperature. So this is the diurnal variability, but I'm also interested in day-to-day variability. And when I looked at variations across individual days, we see that the urban dry island has a more significant impact on the UHI on the hottest days. So just focusing on this plot to the left first, this is a set of daytime averages. So each dot here is a day. And we can see that the magnitudes of the urban temperature island and urban heat island have opposite relationships to the magnitude of the absolute dry island. So the stronger your daytime absolute dry island, generally the stronger your temperature island will also be, and the higher temperatures will be in general. But the closer your UHI will be to 0. So this is more evidence that the urban dry island is having this moderating effect on the UHI. And again, that I'm using UHI to talk about relationship to impervious surface cover. So This is important because on the hottest days, when we might care the most about being able to predict really accurately which parts of the city might have extreme heat, might be experiencing extreme humid heat, that is when we're likely to see the biggest difference between what the urban temperature island looks like and what the UHI looks like. And so we might see a really clear relationship between temperature and impervious surface cover on these like heat wave days. But if we look at heat index, we might not see a very clear relationship to impervious surface cover at all. And that's not to say there might not be other variability in heat index. It just means that it might not be primarily driven by impervious surface cover. There might be something else going on. And this is because of that influence of lower humidity in highly impervious areas. Now, looking at the nighttime, there is some evidence that nighttime heat exposures might be where health impacts are felt the most. And at night, the absolute dry island is essentially zero. And so it has very negligible effects on driving any difference between the UTI and the UHI. So this is all to say that if you care about daytime heat exposure in the summer on really hot days, humidity is going to matter a lot, and it might really change the spatial variation in temperature or in heat index across the city. But if you care about nighttime exposure, you probably don't need to worry about humidity too much. So to summarize, yes, Baltimore does have an urban dry island, especially on hot summer days. With this urban dry island, when we have much lower specific humidity in highly impervious urbanized areas, even when the temperature is slightly higher there because of the UTI, that low specific humidity is going to bring down the heat index there and wash out any change in heat index with impervious surface cover. Importantly, this effect is strongest on the hottest days. So this really underscores that it's important to take spatial variability and humidity into account for planning around daytime extreme heat exposures. So I'm wrapping this work up right now, but in the future, I'm interested in looking deeper into a mechanism that might be driving the urban dry island, maybe looking at latent and sensible heat fluxes from the surface at a couple of the flex tower sites that we have. And then also another dimension of this is that heat index itself is a pretty limited metric. We are also like human heat exposure is also heavily influenced by things like shading and wind speed. And so in the future, it might be interesting to look at more complex heat metrics like wet bulb globe temperature that also take those things into account. And so with that, thank you to my research group at Hopkins, the many, many BSEC folks who have given me feedback on and help with this work, and especially the people who are out there putting up weather stations and maintaining them and getting kids to interact with them. Also the weather station hosts themselves. And with that, I would love to take questions.
Thanks, Izzy. That was great. We've got time for a couple of quick questions. Does anyone have a question? Jason.
Oh, great job, Izzy. All right, annoying question. We have folks who want to plant more vegetation, more green infrastructure, more blue infrastructure. It's going to solve our problems. Well, you're just kind of showing that actually it has the potential to raise the moisture content in the urban space and maybe with it heat stress. But I mean, it's not quite that simple. What do you think about all that, Izzy?
Yes, thank you for this question. This is really important because I don't want this work to be interpreted as saying trees are bad. Trees are very good. Vegetation and trees are very good for a lot of reasons that have nothing to do with climate. But also, this work might be saying that, summertime, middle of the day, on the absolute hottest days, lower humidity might be a good thing for heat stress. And that's heat stress relative, like in urban areas relative to rural areas. Like we're still talking about miserable amounts of heat. We know how Baltimore gets in the summer. But that's like one very specific part of this result. There's also a lot else, um, like other times of the day where that result isn't necessarily true. Um, and so this might just signal that maybe in highly urbanized areas, something like shading might be a more effective heat mitigation technique, but trees and vegetation are still really good in a lot of other situations for reasons not related to climate. And they also do things like trees can also provide shading. So yeah, I don't want this work to be interpreted as trees bad because they're not. They're great.
Ying?
Hi, thank you for sharing the interesting results. I seem to recall that in your uh, heat index plot, and there is a 12 in the middle of the day, and then it's actually higher, almost say nighttime or so. Yeah, this one, the left one.
Oh, here?
Yeah, the one on the left. I think I do you think that kind of has anything to do with like what I have seem to have heard from the health people saying that actually the risk for people to experience like some of the uh, urban heat island related health risks that's actually is highest nighttime, not really the hottest daytime.
Yeah, absolutely. So during the nighttime, because there's not really any urban to rural difference in specific humidity, the UHI basically just looks like the UTI. So temperature and heat index kind of follow each other. Obviously, the heat index might be different based on what the background humidity level is. But this is definitely saying that we still have a clear urban-rural divide in heat index during the nighttime. And so if what you're focusing on is nighttime heat exposures, um, heat index is, I think, still really an important variable to look at because it's closer to what we experience as humans. Um, but spatial variability in absolute humidity isn't going to be affecting the heat index that much at night. Did that answer your question?
Yeah. I'm just trying to think about what I seem to have heard from the health experts. Yeah, they're saying actually nighttime is more dangerous than daytime during
Yeah.
a heat wave, something like that.
Yeah, definitely.
Okay, there's
Yeah,
more questions.
yeah,
Sorry, I'm
I have
gonna.
a quick question, Darren.
Okay.
Yeah, okay. Nice presentation, Isabel. I'm looking at the interpretation of all of this. How would you, let's say you are tasked to speak to, the people. So what would be your best advice in order to mitigate the influence or the impact of its index within Baltimore City?
I think we don't quite know enough about how other things like shade and wind speed affect heat exposure across the city to say for sure. Um, like I said, heat index is it's closer than temperature to how we experience heat, but it's still a very incomplete metric. Um, so something that this work might hint at is that um, maybe um, maybe for middle of the day, summertime heat exposures, something like shade might be really effective for cooling the pavement, and then you don't have so much like sensible heat flux coming off the surface. Um, yeah, but really, that's hard to say anything for sure. We would really need to know more about what is going on with shade and wind speed because those can also impact um, like a physiologically relevant heat as much as humidity, if not more.
Okay, thanks, Izzy. I'm gonna cut this off now because I'm sure a lot of us have meetings we're running to now. But thanks, that was great for both Izzy and Caitlin, and I'm sure both of them would be happy to answer questions if you send them in an email. Okay, thanks everyone.